Okay, this is your chapter 0, and in many ways this chapter is going to be mostly stuff you know, but you haven't probably made these connections yet, because we spent so damn much time teaching you the terminology in math that we didn't get a chance to ever teach you how the hell it applies, right? Okay.
Do you have the slides on Google Classroom yet?
Yeah, they're under a folder, chapter materials, along with the video folder and all that. Okay. So there's two different terminologies. There's two different types of analysis. There's quantitative chemical analysis and there's qualitative analysis. You probably remember this from Gen Chem, hopefully. Qualitative being if it is or is not, right? Quantitative being how much. So the quantitative chemical analysis is going to measure how much of a chemical substance is present. In most analytical situations, this is actually more important because, frankly speaking, there's low levels of uranium, lead, most materials there's low levels of in pretty much any sample you look at, okay? Okay, anyways, we can do this after, we don't have to do it during the lecture. Okay, so the qualitative is going to be, is it present? To be frank with you, in an analytical situation, qualitative usually means is it above or below a threshold, okay? So is it above 1 part per billion? Is it above 10 parts per billion? And you'll have to identify that threshold. For example, the government has a certain level of rat feces that's okay to be in food, right? Why is that? Because there's rat feces in pretty much damn near everything. I'm not joking. You look at any sample, there's probably uranium, there's probably lead, there's probably rat feces, there's probably a variety of things you don't want in it, but they're not in amounts that are meaningful, okay? And that threshold is what determines the qualitative whether it is or not, okay? For example, does it have the color yellow? Well, there's a lot of things that have the color yellow, right? I might cut it off on that examples. Please let me know if I start giving too many examples. I'm going to just say that now and I'll never say it again. I can give hundreds of examples for any topic in this entire course. I just know way too much about this, okay? So this could be never ending. I could probably teach you an entire degree on it, like hundreds of hours of lecture. All right. Now, remember that one of the hardest things in science is not just doing the experiment, right? Because there's a process that leads up to doing the experiment. You have to ask the question, you have to come up with a hypothesis, that can be tested, and then you have to design an experiment that actually tests that hypothesis. All of those things require you to be very careful in your selection of what you're doing, right? Those are things we haven't been able to teach you a lot yet. And this is the class that's going to kind of let you start developing that, okay? Does my experiment actually say no to my hypothesis? Can I say yes to a hypothesis? Is that possible? Can I prove a hypothesis? Come on. Can I prove a hypothesis? I can't. I can never prove a hypothesis. Only thing I can ever do is disprove it, right? Or fail to disprove it. If I fail to disprove it with enough different tests and I run out of things to try testing on, then I go, that's the theory of, right? What happens if something's tested every second of every day? What do I call that? No, if something's tested all the time. Like there's gravity, right? I'm literally testing it every breath I take, every movement I make. I'm testing gravity, aren't I? So what do I call that? I call that a law. Because it's being tested all the time. Okay? Okay, so these are the general steps that are going to happen in a chemical analysis. You're going to notice that they're actually the scientific method. They're just applied. Okay? Formulating the question. Hey, notice first thing, question, right? Selecting the analytical procedures. This is essentially splitting up your hypothesis portion, okay? You'll notice your hypothesis portion actually gets split up into parts of each of these. So selecting analytical procedures. Sampling. Sample preparation. Then you're going to analyze a sample. You're going to report and interpret that data. Notice the framing and interpretation are just as important as the analysis and every other portion of this, okay? If you mess up on any part of that, you are going to give out garbage, okay? You're going to give people misleading information. And that can be deadly. Okay, so, and then finally is drawing conclusions. Honestly, this part, this is the part that it's very rare for the scientists to be able to do. Like, we draw our own conclusions, but let's be frank, the conclusions that usually matter are usually a politician or, business person or somebody else. So there almost should be another step here that in front of drawing conclusion that's presenting it in a manner that makes your case. And this is where an analytical chemist can really team up really well with somebody that's more business-minded, okay? If you can get somebody that's very good at presenting information, it'll really help your life. Okay, so let's give us an example task to do this. So let's determine the caffeine content of a chocolate bar, right? So we have our question now, right? Because we need an example. So what is the caffeine content of a chocolate bar? Cool. And usually the question gets given to you by somebody else, though you can generate your own questions if you're just doing research for your own or grants or whatever. Number 2, selecting the analytical procedures. So this is the part where you're going to start doing a literature search usually, okay? You can do your own analytical procedure, but it takes a lot more time to develop and standardize than to just look it up and find something and adapt. So you first begin with a search for chemical abstracts for an analytical method that will work in the sample you are looking at. So you would want to look for something very similar. If you can find, testing chocolate for caffeine, that's fantastic. But you could also just find testing a homogeneous medium for caffeine, testing a homogeneous medium for an organic acid. Those would all help, right? So you can broaden out the scope more and more if you can't find something, okay? But you need to find something that will work in that situation. Make sure that you understand your system you're looking at. So this is not a water media, is it? If it's a water media you need to do for the test, you're going to have to transform that sample of chocolate, aren't you? Because chocolate is not a water media, is it? Not at all. By the way, you've already been misled on this before. Have you ever tested the pH of like oily substance? You all grew up under me. Most other people would have you test the pH of an oily substance, typically like soaps, directly with no water, or an oil sample. You can't even do it. It doesn't work. So most people are doing a test that doesn't work and in the wrong media, right? And those are labs written by PhDs in chemistry. Happens all the time. You need to look, when you look for this, for keywords. I just did a literature search deal with him, but if you want, I can release a video sometime on how to do a proper literature search. It's a fairly involved topic. It takes a little while to go through, right? So this is sort of basis of it. You have to look up for your terminology. Caffeine, chocolate, you're going to find numerous articles. It's more important to narrow those down than it is to expand those. So if you get 1 million hits, it's useless. It's just going to waste your time. If you get 10 hits, you can go through those, right? And figure out if they're useful or not. It's better to get 0 than it is 1 million. All right, so look for procedures suitable for the equipment in your laboratory. If you need an ICP-MS, which is $500,000, that's probably not a great research to try to do at Bethel, right? No, that would be a really dumb way to try to do it, right? It's not going to work. So you need access to the equipment. Don't try to get procedures that you can't even do. It's not going to help you out. However, if you find those articles, you may be able to look at their citations. At some point, that procedure would have had to standardize against a known procedure, meaning they're probably going to have a known procedure that's different than it, somewhere in one of those articles, okay? If you go back far enough. If necessary, you may have to devise a new procedure to make the required measurements. If you find one for UV vis, you can adapt it for your equipment, because there's many types of UV vis and they all work mostly the same, right? So, however, make sure you stay in your wheelhouse. If you don't understand how the method works, don't try to adapt things you don't understand how they work, okay? Gotta be careful. Do the research and actually test the research against a known sample, all right? It's the absolute most important thing I can tell you. You come up with something new, test it against a known quantity, something you know what it should give you. By the way, there was a new lab procedure we were doing as an undergraduate, or when I was a graduate student, and we were taking they were taking a bunch of samples. They sent us hundreds of samples, weeks worth of just dedicated work. They were all looking really weird, so we went ahead and sent them a sample and said, go ahead and do this one. It was a sample that we'd already looked at with another method, and we knew all the peaks it should give us and where they should be. They were off on every single one. And so we told them their thing's completely miscalibrated. The company that sold it to them for $1 million had a guarantee for its calibration, and that company had to come in and recalibrate the thing over the course of a month. Hundreds of man hours to recalibrate it. I guess they fucked up the calibration. Not the group, the company did. It wasn't calibrated right. Sampling. So sampling is going to be the process of selecting representative material to analyze. Let's think of it this way. If I want to look at the composition of a human being, and I grab a piece of hair, is that going to give me the composition of a human being? No, actually picking a sample for the composition of a human being is going to be very difficult, right? Hell, I could pick a whole human being, right? And what if I get somebody that's missing an arm? Well, that's not typical human, is it? What if I get somebody with a severe mutation? Not typical, is it? There's all sorts of options there. Finding a typical sample can be incredibly difficult. It's one of the most difficult things you can do in psychology and biology, period. In chemistry, we get to sort of cheat a little because we can just take enough sample, randomly sample across it, and mix our samples, right? So you could just take a chocolate bar and melt down the whole damn thing, right? And that'll give you a typical chocolate bar, won't it? But what if it has a macadamia nut in it? Oh, now we're tricky, aren't we? So you gotta be very careful about this. I've actually seen dozens of laboratories that have large government contracts, including a COVID testing laboratory, by the way, and a lead testing laboratory that failed to do proper sampling and got a bunch of wrong results and really caused a mess like worldwide. So I can't really say because they were told to me in confidence. But suffice to say, even the people you think are professionals know what they're doing, fuck this one up a lot. Okay, so again, this is a term that comes from computer science. It's garbage in, garbage out. What it means is if you start with a bad sampling procedure, if you start with bad data going into anything, whether it's a computer model, whether it's a spectroscopy that you're putting it in as a sample and your spectrometer, whether it's a titration, doesn't matter. If you put in garbage, you will only ever get garbage. Okay? There is nothing you can do to improve that. Just start over. Just make a new sample, start over, okay? Do not try to fix shit data, okay? And this is something that's incredibly common. I've seen 100 articles retracted over the last year because of this. Do not fix shit data, okay? Just redo it. It's not worth it. You're just going to make things worse, all right? If you begin with a poorly chosen sample, or if the sample changes between the time it's collected and the time it's analyzed, your results are going to be meaningless. This happens all the time. I know blood samples they took, they have it shipped across country and then shipped back the other way across country, and by the time it gets to them, it's dried blood, and they weren't able to resolvate it properly, okay? Dried blood can be very difficult to work with because it separates, right? Again, you need to make sure, you should have quality assurance checks throughout your sampling procedure, okay? And you should recheck those samples if you come back a week later. Don't just assume they're going to be okay, because they may not. So is all chocolate the same? If you wanted to make broad statements about caffeine in chocolate, you're going to need to analyze a lot of chocolate, and you're going to have some sort of test that can disprove whether chocolates are the same, right? Because that's not true. It's pretty obvious that there probably is other types of chocolate, right? That not all chocolate's the same. You're going to have a way to check that, okay? If you find yourself making broad statements about large populations of anything, you really need to see if you can be wrong, and you need to try to prove yourself wrong. Like, all humans have this feature. You better have a way of trying to disprove yourself, right? Notice, by the way, super common. I've told you probably every single bullet point I've told you on this is stuff you see every day in the scientific community being done wrong, right? Like literally over the last 3 years, you've seen almost every single one of these done wrong. Publicly, in the media, by the entire fucking world. So, you've seen a whole lot of this done wrong, so please don't do it wrong. I'm trying to make you guys better than that. Don't be Fauci. Pure chocolate bars are fairly homogeneous or homogeneous, depending on how you want to say that, depending on what side of the pond you're from. So it's a pretty safe assumption for most pieces of chocolate that testing one side of it is going to be the same as testing the other, but you should not take that as a guarantee, okay? At some point in your testing, you should have some sort of test to determine whether one side is the same as the other, all right? Chocolate with, like, for example, a macadamia nut in the middle is obviously going to be a heterogeneous or heterogeneous, right? By the way, that's European versus English or American English ways of saying these. So obviously, in a heterogeneous material, the sample is going to change from one side to another, or maybe even every millimeter. It could be quite a bit of change. Homogeneous samples, by the way, can be visible to the eye. You can't tell the difference. But they can actually be different from one side to the other. Huh? Sample preparation. Converting a representative sample into a form suitable for analysis is what we call sample preparation. In most cases, this means making it a homogeneous sample. Okay? And the best homogeneous sample to use, deal with, and test is obviously a liquid sample, right? Why don't we want a gas sample? What do gases do when you open their containers? Float off and escape, right? So gas samples are very difficult to wield. Why would we not want, say, a solid sample? Yeah, it could be different throughout. It could have a gradient different, right? But even worse, solid samples are very difficult to get the amount that you need for testing, right? Liquid samples, there's pipettes, I can just, drop whatever I need on it, no problem. Cool. And yeah, how do I mix it? Well, I just mix it, right? I can literally just mix the thing up. How do I make sure it's not heterogeneous? Well, I can allow the other medias to settle, right? So if there's solid bits in it, I can allow that to settle and I can filter it out. Liquid samples are just the easiest one to manipulate, okay? Solid samples are more difficult to manipulate, but you can. And gas samples need to be made essentially where you're going to test them, because they're just freaking horrible to try to keep and use, okay? I did a lot of stuff with gas samples, by the way. They are doable. They have a lot of mechanics that are similar to liquid samples, but you have to have very specialized, very expensive, like tens of thousands of dollars pieces of equipment to deal with them, okay? It's very pricey, very difficult. Samples with low concentrate of analyte may need to be concentrated prior to analysis. If you have too low of a concentration, you may not be able to detect it, right? What about the other way, though? What if it's too high concentration? Yeah, you may need to dilute it as well, right? Now, dilution's actually easier to do than concentrating it, right? So it's easier to dilute than concentrate. Why would it be that you'd have too high of a concentration? Can you think of a time that might happen? But if you're doing like spectroscopy, you have to have a certain amount of light that gets through it, right? So if it's too high concentration, it may just block all light from getting through. Okay? That's typically what happens. It's pretty common for it to give you a signal outside of your responsive range, which we'll talk more about later on. It may be necessary to remove or mask species that interfere with chemical analysis. There are species that can make complexes with other stuff you have in there. There's species that can detect the same as another species, depending on your test. So what you may need to do is mask, which, like a mask, right? Make it so that it's no longer visible, okay? Or that no longer interferes. This could include reacting it with something else. This could include binding it with something else, so it's no longer binding your sample. This can include a number of different ways of doing it, okay? But it's referred to as mask a species. So for a chocolate bar, sample preparation is going to consist of removing fat and dissolving the desired analytes. Caffeine is soluble, and so that's a good way to test caffeine, right? Why would we want to get rid of the fat? The fat is not soluble, is it? So whatever testing method we're doing that's aqueous is going to get clogged up and have a lot of problems with fat that's in a whole nother layer, right? The fat would make it non-homogeneous. Okay, the fat is going to be removed because it will interfere with our chromatography. It'll absorb where it's not supposed to and cause blockages, right? And chromatography would be your easiest way. This is a mortar and pestle. This is one of the easiest ways to grind up materials so it becomes more homogeneous. And you can then do reactions and extractions with it, right? And we've actually done this before, haven't we? We've ground stuff up so we can test it easier. You'll remember it from organic chemistry. Notice this is another part of organic chemistry right here. We literally were introducing you to the basic lab techniques to do this stuff, right? So again, these are an extraction, right? Just a nice, simple extraction. So we have our chocolate finely ground. We have a solvent right here, petroleum ether in this case. We're going to shake it really well so that our material that's in this finely ground chocolate is extracted into our solvent. Then we need to let this solid settle down. We can speed that up with a centrifuge, right? So then we have a packed solid residue that we can get the liquid away from. And so we get rid of the supernatant liquid. This was a petroleum ether, so that is nonpolar, and that means this stuff is mostly fats, right? it won't be an acid, will it? And caffeine is an acid. Okay? Okay. And notice it is the exact same procedure we did. The extraction of an acid. Remember that? An acid residue? Yeah. Organic 1. So this right here is then the residue that is defatted. We remove the fat, right? Okay. Again, this would then be extraction of the caffeine from that residue. We'd get that into something that we can boil the water in. We put it with boiling water. The boiling water will speed up the extraction. We take that extraction. It's going to have some solid particles in it. So we'll need to centrifuge it down to get rid of the solid particles and get the liquid portion. We'll withdraw the liquid portion. We'll inject it and filter it so that we can then use the dissolved caffeine and several other components, usually sugars and such, and put it in a some sort of testing device. In this case, we're probably doing some sort of like gas chromatography or liquid chromatography, depending. Probably liquid chromatography. So one of the solid sample preparations is solid phase extraction. This simplifies your sample preparation by separating some of the major interfering components from your mixture from the desired analytes. Everybody know what an analyte is? What you're analyzing, right? Yeah. That's what you're analyzing. It's one component of the mixture, right? Okay. So an SPE cartridge consists of a short disposable column that contains a chromatography solid phase that can clean the sample enough prior to performing chromatography on an expensive analytical column. Essentially, it's to remove stuff that can block it, so you don't have to clean it so much. Okay? The solid phase extraction will separate your caffeine and theobromine from sugars and fats found in chocolate. And you would, if you just looked at all the stuff in there, you would find there's several different components, two of the major ones being these two. Okay? And so you do chromatography, where things move at different rates through a solid or through a mobile and immobile phase, right? Okay, so this is your conditioned column. Notice columns always need to be conditioned. You remember conditioning, you put in the solvent and you keep it above the level, the solid phase level. Okay, and this allows things to spread through. We then have our desired analytes right here. Notice it's in a mixture. These go through. One of them will move faster than the others. In this case, we have our weak solvent that's going to move the sugars faster and leave the analyte. Then we do a stronger solvent that's going to move the analyte faster than the fat. And the fat will be left behind because we don't care. We don't want the fat. So the analysis, that's the next part. We inject the solution into a chromatography column. It's going to separate the analytes and measures the quantity of each, how much signal we get from each. We measure the concentration of analyte in several identical aliquots, or portions, right? Everybody remembers aliquot? Roughly equal portions that you take of a single sample. The purpose of replicant measurements is to assess the variability or uncertainty in your analysis, and it also guards against just gross error, right? You know, it happens sometimes that you take an aliquot and you think you're taking, 1 milliliter samples, and one of them ends up a 2 milliliter sample. It happens, right? Or you're taking samples and you get your test tubes mixed up and you take the wrong one, right? This stuff happens. So what you should always do is have replicants that you can compare to, and how many replicants do you need to determine whether something is the same or not? What's the absolute minimum? Can you just take 2 replications and call it good? 2 replications is always a line, right? So they're always, you never know which one's right. So you need a minimum of 3. It's the only way you can tell whether they're the same or not. And 3 is not enough, is it? Actually, that question was somewhat of a trick question. Like more than 3 would be the absolute minimum that you could ever do, period. But in reality, there's a statistical test that we'll talk about when we get to the statistics portion that will tell you how many samples you need, okay? And it's based on the uncertainty in your data. Essentially, you need enough that your uncertainty bars don't cover everything, okay? That you actually can start excluding data. That's the sort of broad of it. So the uncertainty of a measurement is just as important as the measurement itself. This tells us how reliable the measurement is. So if I give you that chocolate has a caffeine content of 1 milligram per milliliter or whatever, right? And I don't give you any uncertainty, did I do my job? Not at all, right? You have no idea of the uncertainty of that measurement. It could be plus or minus 100. It could be 1 plus or minus 100, right? In which case my number's fucking meaningless, isn't it? Okay. On the other hand of that, this is something I see all the time, and I just want to warn you off of it. I see people give me numbers that are like, this is when I used to be an editor for a journal too, that is like 1.02567, blah, blah, blah. They have 10 digits behind it, and it's plus or minus 0.1. Was there any meaning on putting anything beyond the 0.1 level? No, that was just silly, right? Yeah. By the way, that uncertainty, you guys have always done that as sig figs before, but now we're going to do actual uncertainty, okay? We're not going to be doing sig figs anymore. You're going to see what the sig figs had behind the hood, okay? Okay, so these are some of the general steps in a chemical analysis. I'm not going to go over this because you guys mostly know what this is. Notice, though, this is a bit different than what you're used to. This one's actually a UV detection. So you've always done it with your eyes. So you did a chromatography column. Notice this is silicon bead chromatography column. You've seen them in lab, but you may not have known it. And you've used something very similar to this. So we have our separation. And then down here, instead of using your eyes, which are not accurate, you use a UV lamp with a detector. So this is essentially a UV spectrometer. Now, keep in mind, you always have to do a limit of detection to determine whether that is or isn't there, right? Okay. And you probably have to calibrate how much of that is there. Okay? Which you guys have done before. You might remember Beer's Law back in the day. Yeah, we'll do that again. Yeah. It's not very different. Here's the spectrometer, by the way. This shows you the peaks coming out of this. See that? And they came out at different times, so we got a very small separation between these two. If you would have tried to do this with your eyes, you probably would have a lot of trouble doing this, okay? Because there's not that much difference in time, right? A couple of minutes. Would have been pretty easy to screw that up. Okay, so calibration curves. In general, analytes with equal concentrations will give different detector responses. These responses may not mean that there's more theobromine than there is caffeine, okay? Because what determines the height of a response, the intensity? Well, concentration's part of it, but there's also the extinction coefficient, you may remember, which is how well it absorbs, right? You may notice that, like, you can have dyes which have huge absorptions, right? You put 3 drops of a dye and all of a sudden you can barely see through your test tube, right? Whereas you can take something else that's colored but isn't a dye, right? And you put 100 drops and, oh, it's barely yellow. That sucked. That's the difference between the extinction coefficients, okay? How well it absorbs that light. And there's similar concepts to pretty much every other signal too, okay? as an extinction coefficient. That's for light absorption, if you're curious. But same thing exists for all the other ways of detecting stuff, okay? Okay, so the response must be measured for known concentrations of each analyte. A graph of a detector response is a function of the analyte concentration, is called a calibration curve. You guys have done this before with Beer's law on a visible spectrometer, okay? You remember where we had like those known concentrations, you took a few of those, you graphed them, you fit a line to it. That's what you're doing, calibration curve, okay? And then you measure your response of an unknown versus that line, right? And that tells you how much of it is. By the way, you have to make new calibration curves for an instrument. You can't use one for one instrument and use it on a different instrument, because every instrument will be a little different, right? Or maybe sometimes really different. So count on it. And don't count on time-wise it staying the same, okay? A good lab will do this over and over, like every day. They'll make a new calibration curve, okay? And you'll find that if you use a calibration curve that's old, you'll experience a ton of problems. Do you guys remember where the spectrometer, I told you guys you need to redo the background? The background is a type of calibration curve, okay? And did you guys ever see where the background wasn't redone? And it like looked bent? It's because it drifts over time. So to construct such a curve, standard solutions containing known concentrations of pure samples like theobromine or caffeine are injected into a column, and the resulting peak heights would be measured. They typically be graphed against a certain function. So for example, straight lines will be drawn through those calibration points. These will then be used to find the concentrations using Beer's law. That's the actual law that this is. Notice that these lines always need to have the y-intercept. You should never ever set that to 0, okay? You know you can fit a line and set the y-intercept to 0, right? Don't do that. The reason you don't want to do that is on any detection method, you could have a non-zero response. And you want to know if that's true, okay? For example, notice this theobromine one right here. That is not 0, is it? Okay? So the baseline with no theobromine in there gives you a non-zero response for this method, right? And it's not unusual for that to happen. It does. There's some reasons, and we'll talk about that in a bit, okay? Okay, does everybody get the calibration curve and see the unknown sample here being fit to it? Everybody's okay with that? Okay. Make sure you pick a concentration that makes sense. You can use any types of concentrations. This one's a part per million, and it gives a wonderful, beautiful, nice looking linear response in the ranges we're looking at. If you were to do something like milligrams per milliliter, these would be like little tiny. All the numbers here would be, 0.000000001 sort of stuff. And you'd barely be able to see anything, right? So be careful with that. It's a thing. And I see people screw that up more often than is, reporting and interpretation. You need to deliver a clearly written, complete report of your results. You need to highlight any limitations that are attached to them. This is true under these conditions, right? And those conditions may not be true. And here's the kicker. If you're in a large enough study or a large enough program, you may not be doing this entire chain. So for example, you may only be doing the sample like after the samples are prepped. The samples may be prepped by someone else. They may be taken by someone else. They may be provided by other people. So you really need to stay under the conditions in which your conclusions are true, because they may not be. Okay. In fact, many, many times, They will not be. And if you don't state, guess what? Everybody else is going to take your analytical report and go, it's a black magic box. It'll always work no matter what we do to it, right? Okay. There's cases where the guy that determined the age of the planet in the 1980s, he had a hell of a time doing it because he didn't know that there's lead that ends up being added to all his samples. So when he tried to determine the lead content, there's always lead there. And that was from the glassware. Finally figured it out, but it took him months. Okay? It was a big deal. So be sure the report is appropriate for its intended audience. This is the two things that are just the absolute most common, happen all the time, screw-ups for analytical chemists. We either don't put in the conditions under which this is true, we don't have a complete report that has the results, how we got those results, and any limitations that would be attached to those results, like if you're doing this to the sample, this is no longer true, okay? If you're leaving the sample for 2 weeks, my lead content to the blood sample isn't true, okay? Because those samples would have separated, all right? On the other hand, you gotta be careful because their audience for your reports, more often than not, are not going to be anywhere near as well trained as you are in analytical chemistry, okay? And so over providing data in the report, essentially the first page, is going to make it meaningless. You really gotta be careful that you give them what they need on the first page and then supplements that they can look at if they need it. Don't think the people you're talking to are stupid. They're not. Well, there's a possibility, but you'd be surprised. More often than not, they are not stupid. They just don't have time to go through a 20-page report to get what they need. Okay? That's more often than not the issue. You give them 20 pages, including raw data, it's like getting 1 million results on the deal they're not even going to look at, right? Kind of like your resumes. Doesn't have it on the first page, it doesn't exist. But, again, if you don't give them enough to tell if it's wrong or right, to tell if there is something that could be interfering, then you'll never know and you're going to give shit data and you won't even know it. Okay? You'll be doing garbage in, garbage out, and you won't even know it's garbage. You'll think it's treasure. All right. Drawing conclusions. So once a report is written, the analyst may not be involved in what is done with the information, such as modifying the raw material supply for a factory or creating new laws to regulate food additives or entire COVID policy. The more clearly a report is written, the less likely it's going to be misinterpreted by those who use it. If you want to see examples of horrific misinterpretations that have caused trillions of dollars of damage and millions of people to lose their lives, you need look no further than sequestration back in the 2010s, the COVID policies for every major country in the entire world, including the CDC response, which is a textbook case of major botches and fuck-ups, unlike anything ever seen in modern day. It's just amazingly bad. Seriously, look up the CDC and how they screwed the COVID response up. It is amazingly bad. Like, it really draws into question the quality of people they're hiring. I think they need to send the whole fucking group back and I can teach them. At least I'll improve it, slightly. This was bad, man. Anyways, sequestration is also a great example where they closed the government down. They shut the government down due to it's actually a letter. It's an economic journal letter. You know what a letter is in a journal? There's articles which are things that have been tested and they think that they've tested it and were not able to prove it wrong, right? And so they've actually done some testing and they could figure out what the hell's going on. And then when you can't figure out what's going on and you're not sure if you're testing it right, you write a letter. And that's essentially saying, I don't have any confidence in these results. I don't know what's going on. Can anybody tell me? Okay? Anybody have any ideas? And so a letter was published by two economists, I think they're from Harvard, and it said essentially that if you go above a certain national deficit, you need to cut off any government activity and get rid of the deficit as much as possible because it'll slow growth for your country. It was wrong. Their spreadsheet just had errors in the spreadsheet, and MIT grad student realized it. But by the time they realized it and anything was done, governments adopted policy based on this, caused trillions of dollars in damage. It was really a major fuck up of the 21st century, like really major one, and by a lot of governments too. Anyways, this is the caffeine content of various different beverages and foods. You can see, success. Congratulations. Whenever you do this, you would want to obviously go ahead and check and see if it conforms with previous results or is in the range. You may not have the same baking chocolate versus Coca-Cola, Coca beverage, pretty different, right? But it's not like it's 1,000 versus 10. You'd expect it to be within a range, right? Factor of 10 would be a high difference, okay? Okay. Does anybody have any questions?
Why is the number T on the logo there? Is that the reason
Oh, okay, yeah, it's formatting. You're going to see that the formatting for my slides is very bad. So the publisher sent me the tables and stuff for my slides. And typically the publishers give me the tables and all that from the book. And this is a good thing to say on presentation and all that. I guess they must have given me these from like an early, before editing was done. And so almost all my tables have something wrong with them, like all over the place. And they never updated these. So I would either have to go and take pictures, which would all end up being messed up because I don't have a professional document camera, which is thousands of dollars, or I have to use the one they've given me. It doesn't really hurt anything. Like, it's not that difficult to figure out. But yeah. You're going to see that all the time, all over the place. I would say at least half of almost all the tables.
I just noticed it right now. It's like, what's T12?
Well, I noticed it looks like blank, but I was like, I looked up and I was like, oh,
No, they're all like this. I'm pretty sure, maybe it's just me overweighing it. It may be, but I'm pretty sure there's a mess up on every single table. Which is easy when you have this amount of data in tables, right? Which is fair. But I wish they would have given me the post-editor copies, because it's not like that in your book. Your book is actually great. Just my tables. Okay.